this video, we're talking about rate of change. So the definition of rate of change is the ratio of the difference in the dependent variables, which are the y, to the independent variables, which is x. So it's the change in the y values compared to the change in the x values. So if you have 2 points that each have an x and a y, and then you have another point that's an x and a y, we would need to distinguish between these two. So just for the general purposes, we will label them x1, y1, and x2, y2. So we have the first point of x and y values, and then we have the second point of x and y values. So to write out in symbols what it means to have a ratio of the difference between the y's and the difference between the x's, that would look like the change in the y values. So you would subtract. Typically we use the bigger y value and subtract the smaller one. And since this is a ratio, we're comparing y to x, so y goes on top and x goes on the bottom. So you would subtract x2 minus x1. So all this means is that you're subtracting your y values, and we only write them in this order typically because if we can, we want to try to subtract the bigger minus the smaller, but it doesn't necessarily always work that way. All this formula means is we're subtracting the y value minus the y value and the x value minus the x value. So notice that since we started with y2, we had to start with x2. So it's kind of the idea of taking this point and subtracting the corresponding values from the previous point. A shorter way of writing that is just the shorthand using different symbols. So remember how I used that phrase, the change in, or the difference in? So the change in y is sometimes shown as this little triangle. This little triangle means delta, which means change in. So that's the change in y over the change in x. Okay, sometimes you won't be given explicit x values and y values to just plug in. Sometimes if you have a word problem, you have to determine which are the x values and which are the y values. So to help you do that, you'll always want to remember that your y values are always the dependent variable. So you're looking for the dependent variable, which would be your y, and your x is the independent variable. Remember that in a graph, you have your x-axis and your y-axis, so that also determines dependent and independent. Independent is always the x values, and your y values depend on the x's, so they are dependent. Same thing if you were to translate that into a table. X is independent, and y is dependent. So this definition that it's the ratio, that means that we have a fraction of the change in y to the change in x. So change in y can also be the little triangle to the change in x. Y is dependent, x is independent. We're going to start with looking at tables to get down the basic skills of finding the change in y over the change in x. So we're going to find these rates of change if they are linear in each table, and we'll talk about what linear means in just a second. So starting with number 1, we want to know what is the change in y compared to the change in x. So our y values, we want to look at them and just see how are they changing. So to get from 15 to 9, what happened? How did that change occur? So from 15 to 9, that went down by 6. And from 9 to 3, how did that change occur? That also went down by 6. And from 3 all the way down to -3, that also went down by 6. So the change in y is constantly -6 or down 6. Okay, now let's look at the change in x. So to get from 1 to 2, how did that change occur? It went up 1, so +1. From 2 to 3, again, +1. From 3 to 4, +1. So the change in x is constantly +1. So our change in y over our change in x, the change in y was down 6 or -6, and the change in x was +1. So since this was a constant rate of change, this is a linear rate of change. So the rate of change is -6, because -6 over 1 is just -6, and this is linear. In example 2, let's look at the change in y. So our change in y is +1. Now we're going to find the change in x. So from 5 to 10, that's +5. 10 to 15 is +5. And 15 to 20 is +5. So our change in x is +5. So since these values changed constantly, that makes this a linear function. Example 3. Again, we are looking for the change in y over the change in x. So be careful of how your table is laid out. We were looking at vertical tables where the y value is on the right and x is on the left. Now it's horizontal where x is on top and y is on bottom. So to do the change in y, we're looking at the bottom row. 7 to 5 is -2. 5 to 3 is -2. 3 to 0 is -3. And then from 0 to -2 is down 2. So notice that this one is not changing constantly. Since this isn't changing constantly, it's not a linear function. In example number 4, let's set up our change in y over change in x. So this one is constant, and the change in y is -1. Then to find our change in x, from -7 to -4, be careful here. Think about if you're on the number line. Okay, if I'm at -7, -6, -5, -4, and so on, if I'm at -7, I'm going to the right 3 times to get to 4, so that's +3. Then from -4 to -1 is +3. -1 to 2, +3. And 2 to 5 is +3. So that is a constant change of +3. Since this was constant for y and x, that makes this linear. And the rate of change is -1/3. Example number 5. We'll go through this one a little bit quicker. From -6 to 2. Okay, from -6 up to +2. If you need to draw the number line, do that. 2. So from going from -6 all the way up to +2, I'm moving right how many times? Okay, now from 2 to 10 is +8, so our change in y is a +8. You don't necessarily have to put the plus in front. Then the change in y is 2. So our rate of change is 8 over 2, but that can be simplified. So if you can simplify the fraction, you want to do that. That simplifies down to 4. And since our rate of change was constant, this is linear. And finally, we have example 6. We want to find the change in y over the change in x. Again, if we can simplify that, we want to do that, so that simplifies to 1. Since this was a constant rate of change, that is a linear rate of change, or a linear function. Now we're going to look at interpreting the meaning of the rate of change when you have a word problem or a scenario and a table to look at. So in number 1, Jamie bought a video game. The table shows her score after playing the game different numbers of times. What was Jamie's average rate of change between game 3 and game 6? So notice that this now says the average rate of change. That means that it may not be constant, but we want to find approximately how many points did her score increase or change per game that she played between game 3 and 6. So remember that we are looking for the change in y over the change in x. And we're looking for it between game 3 and game 6. So for game 3 and for game 6, those are the two x and y points that we're going to be looking at. So if we call this x1, y1, and x2, y2, then we can use our formula to find the rate of change. Now, when you're talking about the formula, really all you're doing is subtracting the y values and subtracting the x values. So on top, we will start by subtracting the bottom number because it's bigger, So 12,485 minus 11,513. And then to subtract your x values, since we started with this y value, on the bottom we have to start with that x value. So 6 minus 3. Now I've got Desmos testing version open so that you can see how to calculate this in Desmos. And all you're going to do is your two sets of subtraction. So 12,485 minus 11,513. And that's 972. So I'm going to go ahead and write that down. So 972 is my change in y. And then the change in x, 6 minus 3 is 3. Okay, so let's kind of pick up where are we in terms of interpreting this. So remember the change in y is the score or in points. So that's 972 points per 3 games, or over the period of 3 games. But we want to know how many points did she increase each game, or per 1 game. So now what we need to do is just simplify this and do 972 divided by 3, and that's 324. So that's 324 points per 1 game, or for each game. Okay, let's look at number 2. During a recent snowstorm, John measured the total snowfall accumulated at the end of each hour. He recorded his results in this table. What's the approximate average rate of change of the snowfall between 1 p.m. and 6 p.m.? So again, notice that this says the average rate of change between 1 p.m. and 6 p.m. So we're going to be looking at what the snowfall was at 1 p.m., what was the snowfall at 6 p.m., and we'll want to find how many inches changed per hour. Okay, so if we're going to look at x1 and y1, x2 and y2, and we're trying to find the change in y over the change in x, we're going to subtract our y values. Typically we start at the bottom. You don't necessarily have to, but whichever y value you start with, you also have to start with that x value. So if we start with 5.1 and subtract 0.7, then on the bottom we have to start with, since we used 5.1, we have to start with 6 p.m. Now, our change in x is an amount of time. We can't really subtract like 7 p.m. or 6 p.m. minus 1 p.m. Sometimes that doesn't work because of our 12-hour clock. When we have 24 hours in the day, but we only have 12 hours on a clock, it's a little bit different when you're subtracting time. So what we're looking for is the change in x, or the change in time. So from 1 p.m. to 5 p.m., how many hours passed between 1 p.m. and 6 p.m., excuse me. So from 1 p.m. to 6 p.m., that's a change of 5 hours. In this case, it would have worked if we did 6 minus 1, but what if it had been 11 a.m. to 6 p.m.? That wouldn't have been the same type of subtraction. We just need to count the hours if we're talking about time. Now we can go ahead and do our subtraction. 5.1 minus 0.7 is a change of 4.4 inches. So it changed 4.4 inches over a period of 5 hours, but we want to know how many inches did it increase each hour. So we'll do 4.4 divided by 5, and that gives us 0.88 inches per hour. Okay, number 3, the population of one variety of frogs in a nature preserve is listed in the table below. What was the average rate of change? So again, this may not be a linear rate of change. We're going to find the average in the population between 1990 and 2000. So we're looking at how many frogs there were over a period of years. So remember, we are looking for the change in y over the change in x. Okay, so 1950 minus 1750, that's a change of 200, but if you need to, you can always type it into Desmos. 1950 minus 1750. So that's 200 frogs over how many years? So from 1990 to 2000, that's a change of 10 years. So this population is growing by 200 frogs every 10 years. So how many frogs per year? Number 4, the table shows the relationship between the time traveled in seconds, which is t, and the distance traveled in meters, which is d, for a car as it accelerates. So accelerates means that it's going faster. So as time passes, it should be getting further. So what was the average speed? Notice that this doesn't say what was the average rate of change. Speed is a rate of change because it's, when we talk about speed, it's miles per hour, or in this case, meters per second. Anytime you have a phrase that's something per something, that tells you that there's a rate of change happening. So speed is automatically understood to be a rate of change. So we want to know what was the average speed or the average rate of change between 3 seconds and 6 seconds. So we're looking at 3:18 and 6:72. Right, 72 minus 18 is 54. So that's 54 what though? 54 meters per 6 minus 3 is 3, but 3 what? Seconds. So the process of interpreting the rate of change. The rate of change is the number itself. Interpreting the rate of change means what per what. Okay, so 54 divided by 3 is 18. So that's 18 meters per second. In number 5, the table below shows the distance Russell rolled a ball after different amounts of time. So it's the distance of the ball after so many seconds of him rolling it. What was the average rate of change? So this may not be linear, that's okay. Between 1 and 5 seconds. Okay, so we're looking at 1 and 4.5, and then 5 and 16.5. Right, so 16.5 minus 4.5 is a change of 12, but if you need to put that in your calculator in Desmos, you can. 16.5 minus 4.5 is 12, but it's 12 what? 12 feet, because that's our y value. Over a period of 4 seconds. So it traveled 12 feet in 4 seconds. So how many feet did it travel per second? Okay, so I want to remind you again, the rate of change is 3, but interpreting the rate of change means 3 what? 3 feet per second. And finally, number 6. Using the table of selected values of f of x, calculate the average rate of change of f of x over the interval where 3 is less than or equal to x is less than or equal to 5. So we are looking for the average rate of change between 3 and 5. So this interval, we've done a little bit with inequalities, so that should be kind of familiar to you. 3 is less than or equal to x, and x is less than or equal to 5. So x is between 3 and 5. So we're looking at 316 and 512. Notice where your x and y values are. Your x is on the top, and f of x is your y. So x is on top, y is on the bottom. So we're still trying to find the change in y over change in x. Okay, our change in y, in this case, look what happens when we start with, if we have x1, y1, x2, y2. If we do this the same way we have been, let's see what happens. So 12 minus 16. And then since we started with 12, we have to start with 5 for the x's. So 5 minus 3. All right, so when we simplify this, 12 minus 16 is a negative 4. And that's okay. That just means that instead of increasing, it's decreasing. And that can still happen with a rate of change. And then 5 minus 3 is 2. So we would just simplify this even more as much as we can. So negative 4 divided by 2 is negative 2. So our rate of change is a negative 2. That means it's decreasing by 2 for every x value. So this is interpreting the meaning of the rate of change. Means you get your rate of change, which is a number, but then what does that mean? What does it represent in this scenario?